Okay, so now we want to talk about the algebra of derivative of functions. Want to talk about the algebra of derivative of functions. And basically we, of course, these are not proved here, but we will have to basically we will have to just take them as they are right now, and then later we might prove them. I don't really know if that's going to happen, but that's the way that, the way that they are right now. It's just some results basically introduced here. So the derivative of the sum of two functions is the sum of the derivatives of the two functions. So the derivative of d by dx of the sum of two functions, for example f of x plus g of x, is the sum of the derivative of the two functions, d by dx of f of x plus d by dx of g of x. So the derivative of the sum of two functions is equal to the sum of the derivative of the two functions. And the derivative of the difference of two functions is equal to the difference of the derivatives of the two functions, meaning that d by dx of f of x minus g of x is equal to d by dx of f of x minus d by dx of g of x. And then the derivative of the product of two functions is given by the following product rule, which is a little bit not basically these kind of make sense that, for example, the derivative of the it's not that straightforward as these two results, meaning that if you have the derivative of, if you have the d by dx of f of x times g of x, that's going to be equal to the derivative of f of x, d by dx of f of x times g of x times the second function plus d by d plus f of x times the derivative of d by dx of g of x. So the derivative of the first function times the second function plus the first function times the derivative of the second function. And the derivative of quotient of two functions is given by the following quotient rule whenever the denominator is not equal to 0. So this is called also the quotient. This is also called the quotient rule, which is basically d by dx of f of x divided by g of x is equal to basically d by dx of f of x times g of x minus f of x times the derivative of g of x, d by dx of g of x, over g of x whole squared. So d by dx of f of x by g of x is the derivative of the first function times the second function minus the first function times the derivative of the second function, and then you have the second function in the denominator whole squared whenever the denominator is non-zero, if basically g of x basically whole squared not equal to 0, of course. So there is a note over here. It says that the proofs of these follow essentially from the analogous theorems for limits. We will not prove these here, as in the case of limits, this theorem tells us how to compute derivatives of special types of functions, the last two statements in the theorem may be restated in the following fashion, which aids in recalling them easily. So basically dy dx of f of x times g of x, you can basically let f of x is equal to v, for example, or you can call this u, and g of x you can call it v, and then u times v prime, meaning the derivative of the product of the two functions is equal to u prime times v plus u times v prime. So this is referred to as the Leibniz rule. This is referred to as the Leibniz rule for differentiating product of functions, for differentiating product of functions or the product rule, or basically also the product rule, and okay, so then this is called the Leibniz rule for differentiating product of functions, or the product rule, or basically the product rule basically. Now the quotient rule is, if I take over here, we said that d by dx of f of x by g of x is d by dx of f of x times g of x, meaning that the differentiation of the first function. So if I take f of x as u and g of x as v, then basically u divided by v the whole prime is equal to basically u prime times v minus v prime times u, or you can write it as u times v prime. That way you can write it, so that's the derivative of the first function times the second function minus the first function times the derivative of the second function uv prime over basically f of g of x whole squared, which is basically v squared, Okay, so now let's derive the derivative of some standard functions, and then basically we will be able to use these in finding the derivatives of other functions, because these basically tend to basically happen everywhere. Now, about the function f of x is equal to x, you know that the product, the derivative of this function is equal to 1. Because basically this is just a straight line. This is just a straight line like this, and the slope of the line everywhere is 1, so then you can say that f prime of x is equal to 1. And it's essentially the slope of this line, and you can read it on the formula as well. Moreover, if you wanted to find the derivative of this function, we said that f prime of x is equal to the limit of f of x plus h minus f of x over h as h tends to 0. So f of x plus h over here would be simply x plus h. So f prime of x is equal to the limit of x plus h minus f of x is basically just simply x over h as h tends to 0, and that is equal to basically h over h is equal to 1. So that's the limit of 1 as h tends to 0, and that is of course equal to 1. So the f prime of x when f of x is equal to x is equal to 1. Okay, so now what we can do, we can use the theorems that we had above about the algebra of basically the derivative of functions, and this derivative that we just found over here, to calculate the derivative of for example, the derivative of f of x is equal to 10x. So you want to calculate the derivative of f of x is equal to 10x, which is the same thing as x plus all the way up to x for 10 terms. Now, of course, we said that basically d by dx of f of x, d by dx of f of x, which you can also write as basically d of f of x, over d of x, is the same thing as d by dx of x plus all the way up to x for 10 terms. And that is the same thing as d by dx of x plus d by dx of x plus all the way up to d by dx of x for 10 terms. And that is the same thing as basically 1 plus all the way up to 1 for 10 terms, which is equal to 10. So we know that this limit may be evaluated using the product rule 2, right? F of x is equal to 10x. And so and set this to equal to u times v. Now we said that basically the d by dx of u times v, we said that basically u was equal to f of x, and if u is equal to f of x and if v is equal to g of x, for example, then of course we said that d by dx of f of x times g of x is the same thing as basically f prime of x times, or you can say that using this notation you can use basically d by dx of f of x times g of x minus what was the product rule? Oh, sorry, not that. That was the quotient rule. I'm sorry. So the product rule was basically d by dx of f of x, d by dx of f of x times g of x plus f of x times d by dx of g of x. So then based on this, if u is equal to f of x and if v is equal to g of x, then you can say that basically u times v whole prime is the same thing as u prime times v plus u times v prime. So this was the product rule. Now the function that we have is 10x, and you want to take the derivative of this function. So I write this as 10x basically whole prime, and this becomes my u, this becomes my v. So then the derivative of 10, is going to be 0, of course. It's going to be 0 times the times basically v, which is times x, and then u is basically 10 times the derivative of v, which is equal to 1, which is equal to 10. Again, the same thing that we got over here. And then using the same kind of logic, we can evaluate, for example, the limit of the derivative of f of x is equal to x squared, which is basically, you can write this as x times x, which is equal to x times x. So d by dx of x squared is the same thing as d by dx of x times x, which is the same thing as d by dx of x times basically x plus x times d by dx of x, So d by dx of x is equal to 1 times x plus x times 1 again, so it's equal to x plus x, which is equal to 2x. So that means that d by dx of x squared is equal to 2x. X squared is equal to 2x. And we have basically, if you want to make it a general thing, meaning that, for example, if you calculate the d by dx of, for example, x cubed, you will get 3x. Over here we had the d by dx of x, we got it as 1. D by dx of x squared, d by dx of x squared, we got it as 2 times x. Now, for example, if you have d by dx of x cube, is d by dx of x cube is the same thing as basically d by dx of, for example, x times x squared, which is, again, you can write it as d by dx of x times x squared plus d by dx of x squared times x. No, let me write it the other way around, so I don't want to confuse you. So time plus x times d by dx of x squared. Now d by dx of x is equal to 1 times x squared plus x times, now we said that the d by dx of x squared is 2x, so that is x times 2x, which is equal to x squared plus 2x squared, which is equal to 3x squared. So then what that means is that d by dx of x cubed is equal to, for example, 3 times x squared. Now if you go for d by dx of x raised to the power 4, d by dx of x raised to the power 4, you can write it as d by dx of x squared times x squared, which is the same thing as d by dx of x squared times x squared plus x squared times d by dx of x squared, which is the same thing as 2x times x squared plus x squared times 2x, which is equal to 2x cubed plus 2x cubed, which is equal to 4x raised to the power 3. So then you can say that d by dx of x raised to the power 4 is equal to 4x cubed. So as a general rule, you can say that if f of x is equal to x raised to the power n, then d by dx of f of x is going to be n times x raised to the power n minus 1. You see over here, using this formula, n times x raised to the power n minus 1 is in this case is going to be basically 1 time x raised to the power n minus 1, which is basically 1 minus 1 is equal to 0, which is equal to 1. Same number that we got over here. In the case of this equation, n times x raised to the power n minus 1 is equal to 2 times x raised to the power 2 minus 1, which is equal to 1, which is equal to 2x, the same number. In the case of this equation over here, n times x raised to the power n minus 1 is equal to 3 times x raised to the power 3 minus 1, which is equal to 3 times n squared. 3 times x squared. And over here, n times x raised to the power n minus 1 is the same thing as 4 times x raised to the power 4 minus 1, which is equal to 4 times x raised to the power 3, which is the same thing that we got over here. So in general, you can say that if f of x is equal to x raised to the power n, then d by dx of f of x is equal to n times x raised to the power n minus 1. For any positive integer n, n, and the proof for this is as follows. Okay, so now to prove this theorem, basically by definition, x raised to the power n, basically the function that we had basically was f of x is equal to x raised to the power n. Now by definition, the derivative of of the function of f of x, basically the derivative of f of x is basically f prime of x, which is equal to the limit of f of x plus h minus f of x over h when h tends to 0. When h tends to 0, which is the same thing as the limit of basically x plus h raised to the power n minus x raised to the power n over h as x raised to as h tends to 0. So now, based on the binomial theorem, you know the binomial theorem, then and the whole basic concept of combination and permutation and so on and so forth, we have basically based on the binomial theorem. You have x plus h raised to the power n is equal to n combination 0, x raised to the power n, x raised to the power n plus n combination 1, x raised to the power n minus 1, h raised to the power 1, plus all the way up to basically n combination n, and this becomes 0, so this becomes a 1, and then h raised to the power n. And now n combination 0 is equal to basically n factorial. I have forgotten the combination. N factorial over n factorial times 0 factorial, which is equal to 0 factorial is 1, and this is basically 1, so n combination 0 is equal to 1. So you can write this as n combination 0 is equal to 1, so that is x raised to the power n. So then you can write x plus h raised to the power n minus x raised to, take this to the other side, becomes x raised to the power n, n combination 1, x raised to the power n minus 1 times h, plus all the way up to basically n combination n, h raised to the power n, which you can write as h times n combination 1, x raised to the power n minus 1, plus all the way up to, and n combination n is the same thing as n factorial, n minus n factorial, and n factorial. So this is 0 factorial, which is 1, and this becomes 1, so in fact n combination n is equal to 1. This part is equal to 1. So then you can write this as n combination 1, x raised to the power n minus 1. I've taken the h out, all the way up to basically h raised to the power n minus 1, basically. H raised to the power n minus 1. So then now I know that x plus h raised to the power n minus x raised to the power n is basically this expression over here. Now over here we said that the f prime of x is equal to this expression over here. So this expression is the limit of x plus h raised to the power n minus x raised to the power n over h, which is basically this expression over here divided by h. Two h's basically will cancel out, and so this expression becomes becomes the limit of n combination 1 x raised to the power n minus 1 plus all the way up to h raised to the power n minus 1 as h tends to 0. As h tends to 0. And so now, in order to take the limit of this expression, what you need to do is well, when 0 raised to any power is equal to 0, so if you were to basically expand this a little bit, you would write it as n combination 1 x raised to the power n minus 1 plus n combination 2, for example, x raised to the power n minus 2 h raised to the power normally this would be h raised to the power 2, so that would be h raised to the power 1, for example, n combination 3 times x raised to the power n minus 3 h raised to the power 2 all the way up to h raised to the power n minus 1. And so over here, for example, if h tends to 0, then this becomes 0, this becomes 0, and this becomes 0. All of these become 0. And then you are left with basically n combination 1, which is now n combination 1 is the same thing as n factorial, n minus 1 factorial, and 1 factorial. And then n factorial over n minus 1 factorial is the same thing as you can rewrite this as basically 1 into 2 into 3 into all the way up to n times basically n minus 1, and n minus 1 factorial, this is just 1. N minus 1 factorial is 1 into 2 into 3 into all the way up to n minus 1. So then all of these terms cancel out with these terms, and then you will be left with n. So n combination 1, which is basically this expression, is just equal to n. So then you can write this as n combination 1 x raised to the power n minus 1 is the same thing as n times x raised to the power n minus 1. That is basically this term over here, and the rest of the terms basically are 0 because h is tending to 0. So then what that means is that you will be left with in the limit, you have only this term over here, which is equal to n times x raised to the power n minus 1. N times x raised to the power n minus 1. And that is basically the limit of the derivative of, that is basically the f prime of x is equal to n times x raised to the power n minus 1, where basically f of x is equal to x raised to the power n. So that is basically what we wanted to prove here. We can prove that also by induction. Induction is also an interesting way to prove things, which is called mathematical induction. So we may also prove this by induction on n and the product rule as follows. So the result, so basically the principle of mathematical induction is basically something that is something simple. Basically, it's basically based on a very simple scenario, meaning that, for example, suppose that you have these blocks over here standing on their edges, on these edges over here. So you have this block over here, you have this block over here, you have this block over here, and so on and so forth. And suppose that you have basically n such blocks over here. Now what we want to do with these blocks, there is a game called, I suppose it's called domino or something like that. Let me see. Domino game, I suppose. I don't know what that's even called. Dominoes. Let me see if that's what I'm talking about.
This might take a couple of minutes. I hope you can bear with me. Double sixes leads. The player to my left has to play a 6. This is neat. I'm going to know everybody's hand. He plays 6-5. You have to play a 6 or a 5. How about that double 5 there? That gets rid of some points for you.
Okay, I don't think that's actually the exact name of the game, but there is a game that you have to basically put these blocks, or these they are like very little blocks of wood or some of made of some other material. You have to just set them one after the other, and then while you're playing the game, it's usually a long succession of blocks one after the other. And then once you're done with the game, then you can basically give the first block, basically you give it a push, and then it pushes the next one, this pushes the next one, and this pushes the next one, and the rules of that game, as I understand it, is that when you push the first basically block, it has to push the next one, the next one, the next one, and so on and so forth until the last block basically falls over. So that's basically how you play the game. And usually what happens is that while you're playing the game, while you're basically arranging the blocks one after the other, usually once you're halfway through the game, then one of the blocks basically falls over, and then the rest of the blocks basically fall over, and then you have to start over and over again. That's something like that. Now we are basically using the same principle as the principle used in that game in the principle of mathematical induction. So what we do in the principle of mathematical induction, so it's some sort of some kind of proving, for example, proving that some result is true. Meaning that first we prove that basically the first case in the case of that particular situation is true. For example, I want to prove that, for example, natural numbers are closed under addition. I want to prove that natural numbers are closed under addition. So the way that basically, you know that we have natural numbers starting from 1, 2, 3 and going all the way up to infinity. So basically, if I want to prove that natural numbers are closed under addition, the way that I should, of course, if I want to prove this for all the natural numbers possibly basically existing, there is really no way to do it, because for example, suppose that I show that, for example, 2 plus 3 is equal to 5, and these two are natural numbers. This is also a natural number. So then again, I have to show it for the next natural numbers, the next natural number, and the next natural number. And the more that I do it, the more I will get more and more and more and more natural numbers. But the problem is that I will never get to the end of the natural numbers, because there is really no end there. The more that you keep going, basically you will get the next one and the next one and the next one and the next one, but the last one you will never reach there. So in such cases, when you have this kind of situation where you can never get to the last of those, for example, natural numbers, what you will do is that you will show that basically this result is true for the first case, or basically for, they call it for P of 1, for example. For P of 1 means the first case in the case of that situation. For example, I show that when I add 1 and 2, 1 is the first natural number, 2 is the second natural number. When I add 1 and 2, I'll get a 3, which is a natural number. So that I call P of 1, which is true. And then what I need to show is that as a result of, so basically now what I've shown is that basically now I've shown that the first block over here falls over. This is basically what it means in the case of this example. I've shown here that the first block does actually fall over, because this is true. The first two natural numbers added together gives me the third natural number, for example. Now, additionally, what I need to do is that I need to show that as a result of each block falling over, the next block will inevitably basically fall over, meaning that I need to basically show that if some P of k is true, if some P of k is true, then P of k plus 1 is always true. Is always true, meaning that if any of these blocks falls over, inevitably the next block will fall over. So I show this, for example, we usually pick some k over here, and we assume that basically the case is true for P of k, and then we prove that the same result is true for P of k plus 1. So now what I have done is that I have shown that basically the first block falls over, and also as a result of any block falling over, the next block will inevitably fall over. And that basically means that, based on the principle of mathematical induction, that means that basically if the first block falls over, and so because I've shown that if the first block falls over, the next one will fall over, and the next one will fall over, and so on and so forth, then I can deduce, or I can actually conclude, based on the principle of mathematical induction, that the last block over here will inevitably fall over because of basically this process that we went through. That's basically the whole logic behind the principle of mathematical induction. So now let's see how they have done it in the case of this example over here. Let's see how they have done it here. So basically based on by induction, we can prove this way. So we want to, so basically we know that d by dx of basically x raised to the power n is equal to d by dx of x times x raised to the power n minus 1. X times x raised to the power n minus 1, which is equal to d by dx of x times x raised to the power n minus 1 plus okay, so here you need to use the product rule. We said that basically if you have for example two functions f of x and g of x, and if you have the d by dx of basically f of x times g of x, then this is going to be equal to d by dx of f of x times g of x plus f of x times d by dx of g of x. So that's basically that was called the product rule. So we are doing the same thing over here. D by dx of x times x raised to the power negative x raised to the power n minus 1 plus basically x times d by dx of x raised to the power n minus 1. So this is by the product rule. By the product rule. By the product rule. Now, by induction hypothesis, we are going to actually, I think we are going to assume that d by dx of x raised to the power n is going to be equal to n times x raised to the power n minus 1. I think that's going to be our hypothesis. And that's basically what I said about that p of k, that you assume some p of k is true, and then based on that you prove that some p of k plus 1 is true. That's basically, and that is basically called your hypothesis. And logically the hypothesis over here must be what you want to prove, which is basically d by dx of x raised to the power n is supposed to be n times x raised to the power n minus 1. So if that is the case, then I suppose I can write this as basically instead of d by dx of x raised to the power n, I could write basically 1 times the derivative of this becomes d by dx of x becomes 1 times x raised to the power 1 minus 1, which is equal to 1 times x raised to the power 0, which is equal to 1. So that is the same thing as x raised to the power n minus 1 times x times, now this becomes n minus 1 times x raised to the power n minus 2. N minus 1 times x raised to the power n minus 2. Right? And there is a plus sign somewhere over here. There's a plus sign over here. So so this is basically the two parts of this thing over here, and then let's see what we get over here. So you have x raised to the power n minus 1, x raised to the power n minus 2, and you have an x over here. So you have, if I multiply this So suppose that, for example, you have so x times x raised to the power n minus 2 is the same thing as x raised to the power n minus 1. So that is x raised to the power n minus 1 plus n minus 1 times x raised to the power n minus 1, which is equal to x raised to the power n minus 1 times basically n minus 1 plus 1, which is the same thing as n times x raised to the power n minus 1. And so now basically we assume that we basically our hypothesis was that d by dx of x raised to the power n minus 1, x raised to the power n, d by dx of x raised to the power n is equal to n times x raised to the power n minus 1. And once I made that assumption, d by dx of x raised to the power n was ultimately equal to n times x raised to the power n minus 1. So this basically supports your hypothesis. So that's basically how the mathematical induction works, although here it's a little bit, I don't really understand how they have used the method of mathematical induction here, because the way that I understand it, it's a little bit more systematic. Here, it's been used a little more in a more subtle way or something like that. So, but anyway, that doesn't really matter, and basically, what's important here is that basically we prove this using some other way as well, that d by dx of x raised to the power n is equal to n times x raised to the power n minus 1. That's basically what's important here. And as a remark, it says that the above theorem is true for all powers of x, that is, n can be any real number, but we will not prove it here. So n can be, it says that n can be, it says that the above theorem, because previously we said that n can be only a natural number. The above theorem is true for all powers of x that is, n can be any real number, n can be any real number, but we will not prove this over here. But well, of course, you can use it for any real number if you need to, of course. So that's basically the whole story here. So this was basically this part was the algebra of derivative of functions. In the next video, we will talk about the derivative of polynomials and trigonometric functions. So I'll see you in the next video. Thank you.